Welcome back to Made Easy Academia. So we still discuss about some problems related to binomial expansions. So let's take a look at some problems from these the past questions. They said if the first three terms of the expansion 1 plus px raised to the power of n in ascending order, power of x are 1 plus 20x plus 160x squared. They now ask us to find the value of n, and p. This is also a straightforward problem. It is just like you are going to use the knowledge of binomial theorem, binomial expansions, using the knowledge of combinations. I told you earlier. Now, if you have this, they said if the first three term expansion of 1 plus px raised to the power of n, meaning the first three terms of this expansion, that is 1 plus px raised to the power of n, if it is equal to 1 plus 20x plus 160x squared. So how do we go about that? Recall that I told you if you are using binomial expansions, the thing is the first one will be decreasing, then the second one will be increasing. Hope you remember that. So now let's plug the values. Now the first number we have here is 1 and the power begin with n. So meaning we have n combination 0, 1 raised to the power of n, then we have px raised to the power of 0. Just like the way we do that expansion, that if I have something like x plus 2 raised to the power of 3, I told you the combinations value will start from this power. This first x here, the first time here, we start from this power, and the second one will begin from 0. Meaning that we have 3 combination 0, then x raised to the power of 3 and 2 raised to the power of 0. Just like the way we do it here with the previous example, that's what we apply here now. We can see here, the power that we have here begin from n. That's how we have n combination 0. So we know this first time here we begin from this power, which is n. That's how we have 1 raised to the power of n. Then we have px raised to the power of 0. Now, so for the second one, so the time will be decreasing. We have n combination. After 0, we know we are going to 1, right? So n combination 1, then 1 raised to the power of n minus 1, then px raised to the power of 1. You see, the first term is reducing by 1, 1. The second time is increasing by 1, 1, just like what we did in the previous examples. Now, plus the third one, we are going to have n combination 2, 1 raised to the power of n minus 2, then px raised to the power of 2. So we can see this is the first time here. The first time is this, the second time is this, and the third time is this. So the first time we have is n combination. Let me just indicate it to make it more easier and more interesting. This is the first term, this is the second term, and this is the third term. Just like the way they stated in the problem, that the first three terms. So which means you don't need to go further. So we are given the first three terms here. This is the first term, this is the second term as well, this is the third term. I hope you are following. So now we make use of the combination method. You know, I told you any number combination 0, of course, is going to be that particular number. So it is 1. Like if I have 5 combination 0, I know that one is 1. We have done that one earlier. Let me show that. If I have 5 combination 0, for example, you know, this is our n here, and this is our r. Remember the formula that we normally apply. N combination r equal to n factorial, n minus r factorial, r factorial. So here, our n is 5 here. It is 5 factorial divided by 5 minus 0 factorial is 0 factorial. So which means this is n factorial divided by, so 5 minus 0, of course, we have 5 factorial is 0 factorial. So now, under this permutation combination, under factorial method, when we have 0 factorial, you don't need to confuse yourself. That one is always 1. So now, 0 factorial here, that one is 1, meaning what I have left is n 5 factorial divided by 5 factorial. Of course, that one is 1. So even if they said 7 combination 0, that one is 1. Even if they say 10 combination 0, that one is 1. So anything combination 0, as far as numbers, which is greater than 0, that one is going to be 1. So similar case will applicable to when we have n combination 0 as well. How? We can have, let's show it here. How is it going to be 1? N combination 0, meaning here, this is our n, and this is our r. I hope you are following. Now, using the same logic, our formula is n factorial divided by n minus r factorial, then r factorial. So now, if I substitute the values, we have n factorial divided by n minus, so our r here is 0, according to what they give us here. That is 0 factorial, then 0 factorial. So here, we can have the result of this will be n factorial divided by, now, n minus 0 factorial. Of course, we are going to have n factorial. 0 factorial, that's going to be 1, as I mentioned it here. So n factorial over n factorial, that is equivalent to 1. We can clearly see. So when we have n combination 0 now, of course, that's going to be 1. So let's substitute the values here. So n combination 0 now, and we have that one to be 1. Now the second one, they say 1 raised to the power of n. We know, even if they said 1 raised to the power of 1,000, just like we were to multiply 1 in 1,000 times, which is 1 raised to the power of 1 times 1 times 1. So even if you multiply 1 a million times, that's still going to be 1. So meaning, if I have 1 raised to the power of n now, of course, what is going to be the result? Yes, exactly. So 1 raised to the power of n is still going to be 1. And note, the second one, the third one we have it, they say px raised to the power of 0. Of course, if I have p raised to the power of 0, there is law in indices that if I have a number raised to the power of 0, that's going to be 1. Like if I have 5 raised to the power of 0, which is going to be 1, or 10 raised to the power of 0, which is going to be 1, or 1,000 raised to the power of anything, even p raised to the power of 0, that one is equivalent to 1. So meaning, if I go back here, so the px raised to the power of 0 here, of course, our answer is still going to be 1. Now, for the second time here, just like the way we did earlier, just like the way we have n combination 0, which is 1, any numbers combination 1 is going to equal to that value. Like if I have 5 combination 1, that one is 5, or 5 combination 2, that one is 10 combination 1, that one is 10, or 100 combination 1, that one is 100. But the thing is, you can see in this case, what we have is alphabet, not a number. So how can we decrease when we have an alphabet? How can we have the terms to be in form of a series? How can we have the term, for example, let's say, from here, I know that if I have 4 factorial, just like what we discussed earlier in the previous example, that if you have 4 factorial, that one is nothing but 4 times 3 times 2 times 1. So what if we now have an alphabet, not a number? Here if you have a number, I don't have any problem with that. So what if you have an alphabet? Like if I have, let's say, x factorial. If you notice this first one here, you can see the term is decreasing by 1 from 4, 3. It repeats itself for the first one, isn't it? So that's the same logic of how I will decrease this one. That means if I have x factorial, is nothing but x, then x minus 1, x minus 2, up to where I'm going to, x minus 3, like that, because the term 2 will be decreasing by 1. The case that we have for when we have the term to be in numbers, it's also applicable to when we have it to be an alphabet. The same logic, the same tactics, and the same process. Now if I have like a n combination 1 now, n combination 1, let's see how we are going to do that. N combination 1, here our n is n and our r is r. Our r is 1 here. So if I apply the formula, n factorial divided by n minus r factorial, r factorial. So now my n is n here. If I substitute, that's n factorial divided by n minus 1 factorial, then 1 factorial. Just like we said, 0 factorial is 1. As well, if I have 1 factorial 2, is also 1. So here we can have this to be n factorial divided by, now 1 factorial is 1. So that means what I have left is n minus 1 factorial. You can see this cannot cancel this because we have to decrease the term until when we have a term that we can cancel. So recall I told you here that if I have x factorial is the same thing as x minus 1, like that. So that means if I have n factorial 2 n factorial is also n minus 1 up to the term I want to decrease the term onto. You understand? So now, if I have n factorial now is nothing but n minus 1 factorial all over n minus 1. So why do we stop here? Because the term that we have at the denominator is equivalent to n factorial. So I have to stop so that they can be able to cancel each other. So if this cancel this now, what we have left is n. You can see the beauty of maths there. So that means they ask you that 5 combination 1 now, that one is 5. 10 combination 1, that one is 10. Even 1 million combination 1 is still going to be 1 million. So now, which means n combination 1 now is still going to be n. So now we can substitute it now. So we can substitute this. So we have to break it down. That's why you have us here. So now plus. So for this one, we are done with the first one. So n combination 1, that one is n according to what we got now. As I told you earlier, when a 1 raised to the power of anything, like maybe 1 million or alphabet or the numbers, automatically is going to be what? Yeah, it's going to be 1. So if I have 1 raised to the power of n minus 1, is nothing but 1. So px raised to the power of 1, you know that one is 1 as a power. That is still remain as a px, then plus n combination 2. Let's quickly show that one because this is a made easy academia. We want to make everything easy so that you'll be able to know how we get the result. So let's see how we can make use of n combination 2. How can we get the result of that one?